Good afternoon, everyone, and a very warm welcome to our April 2025 Bite-Sized Corrosion series. And we're going to spend some time spotlighting corrosion failures. I'm Vanessa C.D. Fisher, and it really is my privilege to host today's conversation. It's our hope that you're going to leave us today having learned something new and eager to continue your journey in understanding corrosion a little more. I thought with it being the 1st of April, it might be appropriate to title this "Don't Let Corrosion Make a Fool Out of You." During this series, we're going to be looking at some corrosion failures. Try to determine what happened, how did it happen, why did it happen, and how can we prevent that happening in our future. So if you've just encountered your first corrosion-related failure, or if this is a topic you know very little about, we know that you're going to find some valuable insights during today's discussion. And in today's discussion, I'm delighted to have joining me Neil Webb. He's very well known to all of us at Bite-Sized Corrosion. And as always, Neil, thank you for your willingness to share the depth of your experience with us related to both corrosion and evaluating corrosion failures.
Thanks, Vanessa.
Now, Neil, whenever there's a failure in infrastructure, it induces a pretty standard panic response. We enter fight or flight, and most of us fight. And so I thought it might be worth talking about some of the do's and don'ts to stop us being labeled fools.
Well, I think the most important aspect of any failure situation is that you should not interfere with the evidence. And that sounds very much like a criminal court case situation. And it is very similar, except, of course, that it's not a criminal situation. Well, it may become a criminal situation. But the challenge with any failure is to find out what went wrong. Something must have gone wrong because we don't design things to fail. And so a failure usually occurs because something has gone out of limit or overload or something like that. And usually there is more than one factor that contributes to the failure. And often you find that there's a whole lot of contributing factors, which when you add them together becomes an overpowering situation, if you can call it that. And for me, the most frustrating thing in a failure investigation is when I get a call or an email or whatever it is saying, "Please, can you help us? We've had this failure. Here's some pictures. We've cleaned it up for you."
Mm-hmm.
And in cleaning it up, the well-meaning person has actually removed a lot of vital evidence or vital clues or indications that would help us to determine what caused that failure.
And instinctively, we want to clean it up, don't we? We want to make it all right as quickly as possible. So it is quite a determined effort to not destroy the evidence. And also, if it's not something you really know about, you don't know necessarily what constitutes the evidence as well. So something that we may think is insignificant may in fact be significant. And Neil,
yes, that's very true. And also the other thing is time. It is very important to get to see the components that have failed or the situation that has failed as soon as possible. And of course, there are situations where that is not practical. You may have had a pipe failure or a pipe leak which has spilled a dangerous chemical. You've got to clean that up. You can't leave it.
Mm-hmm.
But in doing so, you need to try and preserve the point of failure.
Yes.
And the other thing that often happens is that you ask to investigate a failure and you get to the site and they've already welded a patch over the leak.
Can't see what caused it.
So, for example, on a pipeline, I'll just use a pipeline leak as an example. A pipeline can corrode either from the inside or from the outside. It doesn't matter which way it corrodes in terms of it'll eventually get to a point that's so thin that it bursts and you get a leak. And if some well-meaning person comes along and quickly plugs the leak, either by ramming a wooden plug into it or welding a patch over it or whatever, you get along there and now you don't know whether the leak was from the outside in or the inside out, the corrosion. And
Yes.
you can tell that just by looking at it. if you can,
if you can see it.
if you can get there to see it, yes, yes.
Mm.
And of course, it's a very, very different situation because external corrosion has no effect on the internals of a pipe and vice versa.
And talking about that, Neil, is sort of like assigning the, let me say, the blame. If we think back to when we were children and something went wrong, our instinct is to respond, it wasn't me. And this response seems to follow us into adulthood. Have you found that that can prevent the correct determination in a failure investigation?
Yes, it certainly can. And your response often is that, well, as you say, it wasn't me, or it wasn't our system, it was your product. That's one of the favorite ones. And the challenge is to get to the correct information about what actually happened. And so you need to go and do a bit of digging into history. And so, just to illustrate that in an example, several decades ago, I was involved in a situation where a waste yeast tank at a brewery had been coated. The external of this tank had been coated as part of an overall plant upgrade situation. And we got a call from the engineers, the maintenance guys saying, you better get your backside in across here fast because your system has failed. In other words, implying that either the coating was wrong or whatever, your system has failed. So we go along there and say, well, what's happened? He said, well, look, go and have a look. The coating is hanging off in festoons. So we go along, have a look at this. And it appeared from just looking at the vessel that whatever was in this vessel had overflowed and attacked the external coating. So we went back to the plant operator engineers and said, well, from the appearance of the tank, you've had an overflow. They said, no, it can't be an overflow. We've got level controls. And they showed me this wonderful control system in the control room with remote sensing of the level of the fluid in the tank and so on. So when you go to do these things, one of your most important things is your eyesight. And you need to look, and you need to look critically. And when you look at something and you can see the evidence of liquid having flowed over a surface, it's very difficult to ignore that. So anyway, we went along and we got to speak to the coalface personnel as opposed to the management personnel, and went and had a chat to the operator, one of the operators, particularly if you get to talk to the people when they are not necessarily on duty, so they don't feel as though they are being interrogated, because, as you say, there's always the "it wasn't me" instinct. That's just part of our nature. So we said to the operators, how do you control the level in this tank? And the operator said, we understand you've got these level controls and so on. So he says, oh, no. We just look out the window. And when the tank overflows, we close the valve. And so the problem was that this product had a very high alcohol content and was a very effective paint stripper. And the external of the tank had not been designed for immersion in waste yeast concentrate, let's put it that way.
Oh, goodness. Yes, and it seems as though we don't always understand, maybe at operational level, the implications of our actions. And that did seem like a very functional way to control the level in the tank, I'm sure. And as you rightly say, management were blissfully unaware, perhaps no longer. Neil, in that case, obviously, when you went to site, there was evidence there, coating hanging off. And you've indicated that we shouldn't be destroying the evidence because that is sort of absolutely key. And I guess the response to that then should be, what should we do? Obviously, I would think call for help from some technical expert, but what expectations should we have of the investigator to be confident that they know what they're doing?
Yeah, so that, of course, is a very difficult situation because who do you call? If you're dealing with a coating system, do you call somebody from this coating supplier? Do you call a process person? Do you call a lawyer? The lawyer, obviously, I would say, is the last person you should call. But the challenge is finding somebody who has a wide range of experience in corrosion. Now, we are talking about corrosion failures in this situation. Corrosion covers a very, very wide range of subjects, as we have seen over these discussions. It could be a metallurgical corrosion situation. It could be a coating that has failed. It could be a rubber lining that has failed. It could be a process parameter that has actually gone out of range, which has caused the failure. When you go as an investigator, for want of a better word, the most important thing is to not go in with preconceived ideas, because you can listen to a description of a situation, you can read a description of a situation, you can look at pictures that somebody sends you, and those will tend to give you an indication what the problem is. But you must be very careful not to have made up your mind before you get to site. So when you go to site, you've got to now look for the details. And often it's the small details that give you the clues.
I think that's something that we tend to perhaps underestimate, that very often the final determiner was something, literally the stone in the shoe, the final piece of straw on the camel's back, just something perhaps out of the ordinary that came in. And I think you're right, going in without a preconceived idea and willing to consider all the options is probably quite helpful.
A good example of that situation was an investigation that I did a number of years back as well, where a sensor that was used in an electrolytic chlorinator failed. So a chlorinator is used in a seawater system, and it is used to generate chlorine gas, which then acts as a biocontrol agent in the cooling system. And this system was then controlled by various sensors. And any sensor that you put into a liquid has got an interface. And in this case, the interface was a Hastelloy diaphragm. Now, Hastelloy is a very, very high alloy material with very, very good corrosion resistance. And there's absolutely no reason why Hastelloy should fail in contact with seawater. So we went and had a look at this diaphragm, and it was pitted. And the pitting was restricted to the exposed area of the diaphragm. And there was no evidence in the situation of any malfunction or anything like that. And we said, well, actually, what was this chlorinator connected to electrically? This diaphragm, And we found, after a fair amount of probing, that the diaphragm of this chlorinator was actually connected through to the earth system of the plant. And the diaphragm was actually picking up stray current from the electrolytic chlorinator, and it was being discharged through this diaphragm. So this diaphragm was, because it had been very carefully installed using insulating materials and everything else to prevent bimetallic corrosion effects, had landed up with a stray current corrosion effect instead. So we earthed the spool piece that the diaphragm was located on in order to prevent this stray current from the electrolytic cells from getting through to the operational, the control systems.
And I think that also demonstrates how, going in without preconceived ideas, you were going into a metallurgical failure scenario, and you end up dealing with a stray current scenario, which, if you'd gone in just thinking this is just about metal and reaction, you could easily have missed. Neil, very often we don't know. We've said, who do you call? You call someone in the know. And very often we feel a little concerned that, having now got this scenario, we called in the experts, but what are some of the things that we can do to help the investigation, even if we don't really understand all the processes and questions that are going to be asked? Are there some key things that we can try and gather or put together that might help the investigation process?
I think the most important thing there is historical data. A friend of mine once said about traffic accidents, said traffic accidents always happen when there is a change. So you change speed, or you change direction, or you change your focus, or you change gear, or you change something changes. The environment changes. You suddenly have a slippery road. The traffic light changes. And the data that is associated with that particular operation is critical. Having that data available, it could be temperature data from a process stream, it could be environmental data, it could be inspection records from a quality control plan. We've had several situations where the inspection records have given us the clue as to why something has failed. Maybe at the time of application of a coating, the environmental conditions weren't acceptable or something like that. Making historical data available, I think, is probably what the most helpful thing that I can think of off the cuff. Yeah.
I think that's helpful because I think there's also that sense of being completely helpless when you're faced with a disaster, and sometimes knowing some of the steps that you can take to facilitate the correct outcome can be beneficial. So thank you for that. I know that you've investigated many, many corrosion failures in your career, and I would like us to talk about perhaps other interesting examples that we can. But I do want to just mention that your overflowing yeast tank has elicited a little bit of discussion, and some comments have come through, which I'll just read through. Would the co-exposure to isopropyl alcohol vapor and product not also have affected the coating outside the tank, as there was no hermetical seal given to the overflow of the product?
Sure.
So that's the presence of isopropyl alcohol vapor and the product.
Well, given that in that particular situation, the challenge or the coating failure had occurred very obviously where the coating had been subjected to spillage. I'm not sure where you would get a sufficient quantity of vapor in the external environment. So remember, this was the external of the tank. The tank was situated outdoors, presumably, and it was vented to atmosphere. So any alcohol fumes would have been vented to atmosphere. They wouldn't have collected around the tank. So I don't know that was a factor. The evidence of the situation was that this coating, which was in an atmospheric, a relatively innocuous atmosphere. I mean, the Johannesburg, even the industrial atmosphere is what, C3? The external of a tank is not designed to be immersed when it's standing outside in the atmosphere. So the system just was not designed to withstand those conditions.
Anyway, let's move on from that one. Do you have any other examples that also might demonstrate how you need to look for the detail, look for the out of the ordinary?
Also a brewery story. There was a situation where during a maintenance shutdown, the tanks of a pasteurizer needed to be recoated because they had some corrosion. So it was an immersion condition, hot, and we were given an impossibly short time in which to do this coating operation because the plant was only available for a certain period of time. So firstly, you couldn't go in there, blast clean, and put on a nice epoxy system, which needed 7 days to cure. Again, we're talking quite a long time ago, so fast curing epoxies were not a thing. And so we got the operating parameters of the pasteurizer. We found a material that was suitable for that temperature range and immersion, got applied. And again, within days of the system being put back online, they found the coating floating out of the recirculating system of the pasteurizer. We had a look at this coating, and this coating had been cooked. You could see it. It had been cooked, like a burnt frying pan type cooked. So again, we went to the operators and we said, listen, this coating has been cooked. It has a maximum temperature of 65 degrees. You indicated that the operating temperature of this pasteurizer was 50 degrees or whatever it was. And so something's gone wrong. And they said, what? No, that's impossible. If the pasteurizer goes to that temperature, it will ruin the beer. So we said, oh, well, look, you can't cook. You can't burn a pan at low temperature. That's impossible. So, okay. will you permit us to put temperature recording devices into your plant? They said, yeah, go for it. So we installed a temperature recording probes, and we discovered that during the night shift, the temperature in the pasteurizer went up to 85 degrees C. So if you suddenly found some rather strange tasting beer from that particular plant, there was a good indication as to why this beer had been pre-cooked.
Goodness me. Yeah, I think there are often stories about failures that actually are because operating conditions aren't maintained as they should be. Neil, this has been a fun and interesting discussion. Thank you for helping us to identify some of the key aspects which we often neglect or ignore or just don't consider, and that we should be considering during a corrosion failure analysis. And I'm sure that just with today's conversation in mind, many of us, when we find that we're encountering a failure, will at least know not to destroy the evidence, and if it has to be cleaned up and destroyed, to take lots of photographs of the before, during, and after so that clues cannot be lost completely. So thank you very much for sharing with us. And to our audience, thank you too. And we trust that as you leave us today, that you feel you've benefited from our discussion and that you'll join us again. Until we meet again, have a wonderful afternoon and thank you for joining us.